So let's say that we have some motion. So someone's sliding into place. We can represent it with a video, and that's great. It shows you exactly what's going on. There's a lot of information. And, you know, it's exactly what you would see, but this is not something that you can embed in a lab report or a journal article. So we can describe what's going on with words. Hey, Tom Cruise is sliding to the right at a decreasing rate. And that's good, but it's not very quantitative. So we can do more. What we could do is every interval, say every second, we could plot his position. And this isn't perfect because while the dots do tell us that there's a change in position happening, we don't know whether he's slowing down, moving to the right, or speeding up, moving to the left. So we usually put some time information onto our picture. And then in chapter 1, Knight puts in these green arrows that indicate that you're transitioning from this dot to this dot to this dot. And you might think, well, this is kind of silly. But the important thing is that we can see that the arrows are decreasing in length, which means our speed is decreasing. And in fact, we can draw little tiny arrows that show us how much the speed or velocity is changing. And while we're not going to be drawing these pictures really outside of chapter 1, being able to think about this, being able to visualize or connect to these things is really important, because velocity, which is speed with direction, is important, and how velocity changes is important, and they're not the same thing. So the difference between the green arrows and the yellow arrows is something that we're going to have to learn, we're going to have to get used to. All right, again, this is kind of quantitative, but it's not what you would see in an advanced physics book. But what we can do is we can take this information and abstract it a little bit. We can plot the time as the horizontal axis and the position as the vertical axis. Notice that even though our Tom Cruise is sliding to the right, he's moving horizontally, we have now depicted position as along the vertical axis. And so we're removing ourselves from the actual picture in the interest of trying to depict this as in a useful way. And this is a very useful way. Notice that we just have raw dots. We can connect them with lines that indicates the change in position over time. But what we're doing is all we know is where Tom Cruise is at brief instances in time. Between those moments, we actually don't know what happened between the frames. We probably can assume that everything is nice and smooth, but all we have is information at the frames. And sometimes that's all we ever have. For some measure, systems that you're going to measure, those dots are all you're ever going to have. However, we often assume that everything is nicely behaved between the dots, and so we can guess a function that passes through the dots or near the dots that approximates the motion. The difference between the graph on the left and the right is on the left, we are just specifying specific moments in time, locations in time. On the right, we're extrapolating the behavior between those points. And that's a big deal, because as soon as we extrapolate that, as soon as we make that transition from discrete points to a continuous function, all of a sudden we can do some stuff. So, oops, we can do some math, and there's supposed to be an equation there. Don't worry about it. it's coming. One more representation that we can use, and one that is less visual, or at least immediately visceral, is to plot velocity. So instead of plotting where we are, we can plot how fast we're moving. So the first arrow means Tom Cruise is moving fast and he is moving more and more slowly. And that velocity graph will turn out to be really important. All right. Replay whatever was confusing to you. Come to class with questions tomorrow, and we will talk more about this.